Momentum. Momentum is the tendency of an object to keep moving in the same direction. An object with a big momentum will be difficult to stop, like this train. That is because momentum depends on mass and velocity. Here's the equation to calculate momentum. Momentum in kilograms meters per second equals mass in kilograms times by velocity in meters per second. P equals m times by v. Let's look at some examples of momentum. The rugby player wearing the number 11 shirt playing for the All Blacks is called Jonah Lomu. He has a large mass of 118 kilograms, which is about 18.5 stones, and he can run 100 metres in about 10 seconds, which is a big velocity, especially for a big guy.
118 kilograms, 6'5".
Once he gets going, he has a large momentum and is very difficult to stop.
Danger here, Cullen flips onto Lomu. Lomu steps outside, cuts inside, he's still not down. He's over!
A bullet only has a small mass, but because it travels at such a high velocity, it has a large momentum. This bullet train has a big mass and a huge velocity, so its momentum is massive. The law of conservation of momentum. The law of conservation of momentum states that the total momentum before an event, such as a collision or explosion, equals the total momentum after the event. Note, this only applies to a closed system where no energy can be lost or gained and is not affected by external forces. But also please note, in real life, there's always external forces, mainly friction, but this law does allow us to calculate roughly what's happening. Watch the pool balls in this example being broke. The law of conservation of momentum tells us that the momentum of the white ball after it has been hit will be transferred to the 15 other balls after the collision. If we assume it's a closed system and that the white ball stops dead once it collides, then the calculation would look like this. Total momentum before the collision equals total momentum after the collision. So the total momentum before the collision is just the momentum that the white ball's got. So that's the mass of the white ball times by the velocity of the white ball. And if we assume the white ball collides and stops moving, the total momentum after the collision is the momentum of the 15 balls. So that's the mass of the 15 balls times by the velocity of the 15 balls. Because the mass is now 15 times bigger, the average velocity will be 15 times smaller. Sometimes when objects collide, they join and move off together, like I've shown when this train engine collides with the carriages. I'll use the law of conservation of momentum to demonstrate. The momentum before the collision equals the momentum after the collision. So, before, that's the momentum of the engine plus the momentum of the carriages. However, the carriages are not moving at the start, so it's just the momentum of the engine. The momentum after the collision is the momentum of the engine and the carriages when they have coupled together. So, the momentum of the engine at the start is going to equal the momentum of the engine and the carriages at the end. So that's the mass of the engine times by the velocity of the engine equals the mass of the engine and the carriages times by the velocity of the engine and the carriages. So that's 8,000 kilograms times by 1 meter per second, and that's going to equal 16,000 kilograms times by the velocity of the engine and the carriages. Note, the mass of the engine is 8,000 kilograms and the mass of the carriages is 8,000 kilograms, so the mass of the engine and the carriages is 16,000 kilograms. So 8,000 times by 1 is 8,000, and that's going to equal 16,000 times by the velocity of the engine and carriages. we can rearrange the equation to work out the velocity that the train and the carriages will have after the collision. 8,000 kilograms meters per second divided by 16,000 kilograms is going to be the velocity of the engine and the carriages. So that comes out as 0.5. So you can see the velocity of the engine and the carriages is only half of the engine's original velocity. This makes sense because the engine and the carriage's mass is twice as big as the original engine's mass, which proves the momentum at the start before the collision is equal to the momentum at the end after the collision. Here's a question for you to try. Does this meteorite have much momentum? Answer: yes. The meteorite has a huge amount of momentum because it has a very big mass and a very big velocity. Well, I hope you understand what momentum is, how to calculate it, and how the law of conservation of momentum works when objects collide. Subscribe to the channel and hit the bell icon to receive notifications of future videos. Work hard, be nice, and bye bye for now.